Hi. Hope you're good after yesterday's party. I'm Alexey Zakharov. I work as a core team developer at Unity, focusing mostly on memory and performance optimization issues.
Yeah, I'm Rene. I work as core team developer as well. We're based out of Copenhagen. And we're here to talk a bit about the asset import pipeline and the build pipeline and stuff like that. Actually, I'm supposed that many people showed up, but let's get into that. So what we want to talk about is like how data gets into Unity and flows through Unity, comes in and basically goes out at the other end and comes out as players and applications. What we often see is that it's a bit of a black box to users. Users don't really know much how it works. And like if you want to do it exactly what you need it to do, like it's quite useful to have a bit of an understanding. So we're going to slice this exactly into two sections. Like one about the asset import pipeline, how your data gets in, and another about the build pipeline, how your data gets out. Like I'm going to do the first part, and then Alexey is going to do the second part. Everything starts with the sources, like the assets and the general artifacts that you create inside and outside of Unity. To the import pipeline, this is all immutable data. Like as part of importing, we must not modify that. And this is what you put in version control and share with on the team members. So the biggest and most important collection obviously is the assets stuff, like all the stuff in the assets folder. But also the .meta files that are in there and specify exactly how to take that data and put it inside of Unity. By default, these files are hidden, but you can make them visible by switching to visible meta files in the editor project settings. And the second collection is the stuff in project settings. This is basically all the settings that you configure inside of Unity. It's all a bunch of singletons. And there's no .meta files in there because we always import them exactly the same way. And finally, one thing that users are often not aware of, there's also the stuff in the Unity installation folder, and that also goes into the import process. There's the built-in resources that we ship with all the players, and then there's the extension DLLs that you may or may not use, and we feed them into the import process as well. So all this stuff makes up the source data that we bring into the pipeline. So from them, we generate imports. And the imports are Unity engine objects that basically contain your source data in a processed form, like in a way where we imply all the input settings and do all the number crunching and all that kind of stuff. The key thing is that this is all throwaway data, basically. You can always delete the entire thing and recreate it. It's meant to be a deterministic process. The downside is, of course, it takes a bit of time. So this may actually make it worthwhile to keep the stuff around. Because, well, in a big project, it might take an hour or two just to input that stuff. So all that stuff goes into the library folder. This folder should not be put in version control. It's all generated stuff, and you should not share with other team members. Like usually that has a bad outcome. And like I said, you can always delete the entire thing, open up Unity again, and we'll just re-import. The key file in there is called asset database 3 for some weird historic reason that no one still knows about, probably Joe. So that's just it's a Unity serialized file that is just a flat dump of all the assets, the information about all the assets that are in your project. By the way, there's a tool called binary to text. I'm not sure if you're aware of, which we ship with Unity. It's in the data/tools folder. And for any Unity binary serialized file, you can point that tool at the file and it will produce a text file for it. This is not the same as the YAML file. It has some special things. You cannot feed it back into Unity, but it shows you exactly what's in that file. It can be very useful to look at the internals. So you can just take the asset database and dump it if you want to. The imported data, however, is not stored in the asset database, but rather goes into this weird folder called metadata inside the library folder. Here we store, basically under the GUID of the asset, all the imported data for that one specific asset. Again, it's binary serialized stuff. You can just fire binary to text edit. You see what's in there. So we know where data comes from and where it goes, but how does Unity know what to import and when to import stuff? This thing we call the refresh logic. And by default, this logic is run when you start up your project, when you open the project, or when you switch back to Unity. This is the kind of delay that you notice often, like when you switch to max, and then you switch back to Unity, and there's the slight delay. This is when we go through all the stuff and look at all the things. You can disable that behavior, the automatic refresh and the editor settings, and then do it manually, hitting like Command or Control R or the right-click menu. For big projects, that can actually be quite convenient. So the first thing we do when we do the refresh is we crawl through all the stuff in the assets folder and compare the files that we find to the information we have in the asset database. And then at that point, we know, OK, this has been added, this has been modified, this has been deleted, stuff like that. It's moved around and stuff. We determine that by GUID. So this step, it's usually pretty fast, but like if you have a really big-ass project, it can take a bit. Then next, we compute hashes for all that stuff. So we feed all the source data into a huge hash generator, and that one determines actually whether the things have really changed. Also, this is specifically useful for the cache server, and we will look at that in the next slide. But it's also useful for finding whether assets have really changed and need to be re-imported. So and then next step, like it's optional. Like if you use the cache server, we try to pull the data from the cache server instead of importing it. And then finally, we know the assets which really need to be processed. So we feed them into the import asset step, takes that huge ass list, slices it into batches, and processes the batches, saves the data back out until it has finished all that thing. Right now, that sits in the editor and in your main thread, and you have to wait until it finishes. And then finally, once we're done with all that, we call to the asset post-processing system and tell you, OK, this is the stuff we actually touched. And here, like, here's all this. Yeah, this has changed. So that's a refresh step. So how does the cache server tie into that? The cache server is actually, it's a super simple thing. It's basically a mapping of hashes to binary blobs. And has some bit of internal logic to keep the size bound. It just deletes old stuff after a time, basically. So the key thing is the hash generation. Like everything hinges on that. What we do with the hashing is like we feed all the things into there that may affect the resulting binary blob that we generate during import. And then before we even run that thing, we can determine whether we have that binary blob available or not. So the stuff that goes in there is the path. That may be a bit surprising why the path, but an asset post-processor may work differently depending on where the asset is. So we need to feed the path in there. That also means if you move an asset around, you're actually invalidating the asset on the cache server and have to regenerate it. Yeah, bit of a catch. And then we feed the importer version. Different versions may generate different data. We feed the hash of the entire contents of the source file, the .meta file to get all the settings. And for some types of imports, like texture imports, for example, the build target also matters, so we feed it into there as well. And finally, we have the hash. Then we go to the cache server, say, hey, do you have an asset for me? And if it says yes, we just pull that thing, put it in place, skip the entire import for that asset, done. If not, we run the import process, and then we take the hash and the generated stuff, we push it back up. So the next time someone comes around, looks for the same hash, the asset is there, and the time is saved. So it's a super simple thing, but like in a big team, or if you switch things, the build targets, very often it can save you quite a bit of time. Yeah. So we've looked at the big picture. Let's also look at like how do we actually import a single asset and the steps we do there. So let's say we have a car FBX model in the assets folder. So the first thing we do is we pass it to the post-processing system. It's kind of a counterintuitive why post-processing. I think it's just bad naming, but we call it to pre-process, pass it to pre-process model, and basically before we even look at it, you get a shot at modifying things or doing whatever bookkeeping you need to do. And then the model importer actually goes and does all the crunching. Like we feed the FBX file and the .meta file, which also contains the GUID and contains all the settings. You feed that into the importer, and the importer does its thing. And the model importer, it basically creates just a big game object hierarchy, puts all the components in place, generates all the meshes, animation clips, and whatever it needs to do. And then once that is done, we take the game object hierarchy and we pass it back out to the post-processing system. So you can take that hierarchy, you can take it apart, you can remove components, you can add new game objects, whatever you want, so that before we actually store it, you get a shot at making that thing look exactly the way you want. And then we just store it in the library folder in the metadata thing by its GUID and just blast it out there. So what does there's a bit of bookkeeping here. What does it actually look like, the structure that we have in the library folder for every single asset? There's two pieces there. We have the database record, which contains all the stuff that you basically see in the project browser. So if you select an asset there, or if you go through a folder, we go through the database and just fetch the data from there. We don't touch any asset-specific things. So it has the path and the type, is it a folder, stuff like that, all kinds of boring stuff. And it has what we call representations. This is the stuff where when you go to an asset and you expand it in the project browser, it may have like a model, for example, may have all kinds of like sub-assets basically. And this is what we call representations. And these representations basically link directly to their actual objects that we generated during import. And these are stored in the file, in the metadata folder. Also stored there is the actual importer itself. And this is kind of interesting because when you go to an asset and you see the properties, the import properties, the import settings, what you see there is the actual importer. And what you're modifying there is the actual importer. So you do your thing, you set the settings, and you hit apply, and we save that back out, and we write the stuff the properties that you set, we write that back out to the .meta file and then trigger re-import. So what you added is actually not the sources, you added like an artifact internal to the pipeline, and then we push the data back to the sources. In terms of like how you can alter that process and then hook into it, let's look at a couple options that you have here. These are like kind of the very obvious ones. If you look at the documentation, it's the first thing you stumble across, basically. So we have the asset modification processor, which allows you to modify asset operations like moving, creating, deleting, that are done from inside Unity. There's a bit of a catch. Like if you go outside of Unity and you move something around and the refresh logic picks it up, you don't get notifications with the asset modification processor. Which is a bit weird. I think we can improve that, but this is how it works at the moment. Then you have the post-process all assets callback, which was mentioned previously, which basically gives you a list of all paths that have been touched and exactly what has been done to them. Especially useful for if you have tooling that needs to know exactly, okay, what stuff do I have available, and you don't want to look that up dynamically in the asset database. And then the per process hooks that we have, they only work for certain types, like we have models, textures, and I think animations, audio, and speed trees. So what they do is like before we touch the data, we trigger the on-pre-process thing. You can do your thing. We do the import, and then we pass you the data that we actually generated, which is different for every type of importer. Again, for an audio importer, you get an audio clip, and you can do whatever you want before we actually store it. So that's the very straightforward stuff. One use case we find that users pretty often run into, and which can be kind of tricky, like when you want to define your completely own custom asset type with your own custom data, own processing. Now, the bad news is that right now, with the current incarnation of the asset pipeline, you cannot define a new importer type in script. Right now, you need to hack the C++ source code to actually do that. This is something we want to like improve in the future. Right now, what you can do, however, is two things. Like one is you can stuff arbitrary Unity engine objects into an asset file, like you name it .asset, and just put your Unity engine objects in there using asset database.create asset to create the asset at a certain path, give it an object, puts it in there, and then you can use add object to asset to add additional objects. And so you can have assets that contain arbitrary collections of Unity objects in your source data. This is one way. The other way is you want to bring data straight from the source folder into your resulting game or application. You can do that as binary blobs or text blobs. It's picked up by what we call text script importer. So if you have a file and you give it the bytes ending, we just pass the binary blob as is just straight into your game. And you can use the text asset class, which has a bytes property, to just get that data. Same thing for text. You can HTML files, TXT files, put them there. They go straight into your game, and you can use the resulting assets, the raw data, unprocessed by Unity. So let's pretty much look at the asset import pipeline as it is right now. Let's also look a bit into the actually not that far out future, because we want to get this thing to the next level. There's some things like the waiting, the blocking nature of it, for example. So one thing that we recently prototyped in that is going to go into development pretty soon is that the asset database is going to move to its own process and basically have its own little internal web server and have a REST API. So at that point, it's no longer that you need to use the Unity scripting API to actually get to that information and run in the editor. It's a separate process that you can talk to with standard web tooling. Also, it's asynchronous then, like the editor is decoupled. It no longer runs in the editor process. I think this will make a huge change in just times people spent waiting for the asset import to finish. We also want to make it so that it doesn't have to import everything up front and stuff like that. There's good things coming. The other thing is that right now we store everything by GUID. And that means we can only have a single imported version per asset. But usually you have multiple build targets, you want multiple versions stored. Or if you switch around settings, like frequently you switch to something and you switch back, we have to regenerate the whole thing from scratch twice, instead of like being able to just go back to previous version. So what we want to do is we want to switch to hash-based storage and actually move the thing out of the library folder, where it's per project, and just move it into a central location on your computer. Sort of where the operation of the cache server and the way it operates locally becomes the same. So yeah, that's coming. And that's pretty much the asset import pipeline.
Okay, once all assets are imported and GUI development magic is done, we want to build our player. And it can be easily done from UI or from scripting API, which has different parameters. And one of implicit parameters is player settings, which can alter build drastically. One of noteworthy parameter is development build. So what is the difference between development player and release player? One of the biggest differences is that we don't ship profiler in release builds, and you can do script debugging there. Also, internally, we do differently native memory allocations, and we don't expose any internal errors or warnings to player. Build player pipeline is much simpler than asset import pipeline, and let's look what's happening when I'm building a player. After we verified that we can actually build the player, platform supported, data exists, and no collisions, it's pretty simple. We compile in scripts, switching to target platform, serialize scenes, serialize shared resources, and do post-processing. Let's look closer at these stages. Runtime assemblies compilation. When we compile them, then we compile scripts use in your game. There are two phases of script compilation. The first phase builds so-called first-pass assemblies, and with scripts which belongs to plugins standard assets, Pro standard assets, and iPhone standard assets folder. And when we build all other scripts, main difference between the first phase and second phase is that you can't reference normal assemblies from first-pass assemblies. That makes possible, for example, to use cross-language references. For example, you have C# script, you want to use an Unity script, and vice versa. You can do it by moving one of dependencies to first-pass assembly then. The same technique is used for editor scripts. Once scripts are compiled, we check if layout is correct and compatible between Unity editor and player. So that basically means that you can't use not Unity editor defines for fields definition, and there should be no data that a player can expect which wasn't serialized when building the player. Platform switch. Once all scripts are compiled, we temporarily switch editor to the platform we are building for. This means that library folder representation of assets we want to include in the build should be ready for serialization and should match target platform representation. That means that, for example, textures might be recompressed, audio data might be recompressed and converted to platforms format. This is temporary switch, and we get back to current platform once build is done. Okay, once scripts are ready, data is ready, we can actually serialize our data. First of all, we serialize scene data. This stage has some details. For every scene, we iteratively build GI data. We remove all editor-only objects with other objects which target with such tag. Then we break all prefab connections and instantiate all referenced prefabs into the scene, so scene doesn't have references to any prefabs anymore. And call editor scripts which are marked with post-process scene attribute. Here you can see important detail that any changes during post-process scene calls have no effect to generated GI data. The same is valid for editor-only objects. After that, we collect dependencies. Scene has script dependencies and asset dependencies. Information about user scripts could be used later for code stripping. And what are the asset dependencies? So basically, every game object has component, at least one transformer component, and any other components might be as standard, like mesh filter, mesh renderer, or your own components you wrote in scripts. And they also might reference different assets, textures, meshes, shaders, audio data. So we traverse whole scene hierarchy and build list of used assets in the specific scene. So you can see on this slide that game objects and components are scene objects, and all assets, textures, audio clips, shaders, materials, they're green, and with shared assets which can be used between different components, even different scenes. Okay, once we know what is in the scene and which assets are referenced, we serialize data. Scene objects save it into main data file, level 0, level 1, and so on files. And referenced assets, which belongs to the specific scene, we serialize. They go to shared assets 0 assets, and shared assets 1 assets files. And we don't write data. We don't use into scenes. We write only assets which are actually referenced. So, for example, if in your component or your reference sub-asset, we save only data which is actually used. And to speed up loading, we write assets data in the same order they will be read when loading. This minimizes seek times. We also serialize assets that might be used across the whole games. With shared assets and with assets which are inside resources folder. So we don't know if they use it or not because they can be instantiated directly from resources, load API, for example. And we do the same thing as for scenes. We traverse all dependencies and serialize with into resources.assets file. One more shared data that should be referenced is Unity built-in extra file, which contains all shaders we want to always include in our game. Last step is post-processing. It has some common parts, but mainly it's highly platform-dependent and contains steps which can produce different outputs for different platforms. So let's look into these shared steps. So first of all, we copy data which wasn't modified by Unity with our data in streaming assets folder. So we don't touch these files at all. You can put the audio, video. You don't want to be imported using Unity asset import pipeline. And you can put the asset bundles if you have granularity for your levels and use asset bundles. We also copy all plugins. It might be third-party plugins, VR support plugins, if you turn this option on. Then we strip assemblies. This is a very important part. And what does it mean? So during scene and shared resources serialization, we track all referenced scripts which are used during build and remove all unused managed scripts there. So in case of L2CPP scripting backend, and for example on iOS and WebGL, we can go further and don't include into the build whole engine subsystems if they are not used in the game. For example, if you don't use physics on a mesh, your binary size could be much, much smaller, and you have actually double win, so your distribution size is smaller, and your generated code size is smaller, so you use less memory on the device. This is a bit tricky because if you use, for example, asset bundle system and have your levels outside of your loader, so like basically your game is just a bootstrapper and it loads asset bundle, you should be careful and be aware that some data, some subsystems might be stripped and that might make asset bundles unusable. So to avoid this, we recommend you to use link XML file to specify scripts you want to leave in your game and which shouldn't be stripped. And also you can include like a dummy fake scene in the build which has components from your systems you want to have alive in your game. Like just scene with collider or mesh agent if you want to use this in asset bundles. Okay, next, if L2CP backend is chosen, we convert all assemblies into CPV files and compile them all into a library, which later can be linked with an executable or your binary. So next step is completely platform dependent and gets you as close to target build as possible. So this is actually per platform post-processing. So for example, for desktop platforms, we create a bundle which you can run immediately after build, and it contains executable, all data, all referenced DLLs, native DLLs on Windows, for example, on OS X, it's just .app bundle you can just run straight away. And for iOS, for example, we generate Xcode project which is used to build and deploy your application later. And finally, we call methods which are marked with post-process build attribute. So how can we customize our build pipeline? So actually, we have only 2 entry points right now with a postprocess scene attribute and postprocess build attribute. Postprocess scene attribute allows you to modify scene before data is serialized. You can do different things depending on what you need. So you can add, remove components, game objects. So depending on the build platform you're targeting, or depending on marketplace you're targeting. So you can add ads, logos, whatever you want. And it's also called during play mode, so you can see consistent picture than your inside editor and player. Here is an example of post-process scene where we can just change server URL for our multiplayer game depending on current platform. So post-process build attribute allows you to modify already built player. So this is completely platform specific because layout of output is depends on target platform, but depending on what you need, you can add extra data to your project, encrypt your binary executable, obfuscate or change in any way, like managed assemblies. If you use Mono, for example, you can also run installer and use full C# functionality to do anything. So, for example, you can build Steam package or whatever you want in this script. One of the important part is build reporting. Currently, build report is written to editor log, which you can find either on file system. On macOS, it's based in library folder, and on Windows, it's in local app data folder, or just open file directly from UI. So it contains information about assemblies you're dependent on. It also can briefly describe data size for different asset types and overall user data. One of important things that could be mentioned is build automation. So this allows you to do different things. So if you, for example, have one game which targets different platforms, different markets, you have kind of old school free paid separation, or you target some specific region and you want your game to be built for all of these different kinds of targets. You can simply do that with command line parameters or cloud build, obviously, which can be used in this case as well. So just run invoke Unity with command line arguments where you can specify method. This is a static method in the editor scripts, and basically you just run script inside editor from command line, and where you can do whatever you want to differentiate different builds for different markets or anything. So since 5.0, we have Enlighten in Unity, and it makes things a bit different for build automation. Enlighten requires GFX device to be accessible by Unity, and that's why you can't build your projects if you use GI data anymore with no graphics option. But still, if you have to do that, you can still do that, and we did support of reference and GFX device on OS X, and we can use Warp DirectX 11 device on Windows to make this happen. Let's talk about future improvements which comes from our current weak points. So data compression. After some work was done for LZ4 compression of asset bundles, which will be in 5.3. We want to use the same for data folder, which is shipped with Unity player. This will be done for all platforms, WebGL, Android, whatever, so we can unify our loading pipeline a bit, and so gives you a bit more performance when loading compressed data. Also, we have plans to extend the build report you can receive after build is complete. So basically, you could see resources which were inside build and actually analyze data size they have in player, and like other data like compression ratio per asset. So we want to eliminate platform switch, that comes from REST service asset import pipeline Rene mentioned before, and parallelize builds. So actually, right now we do it incrementally. So like we build scenes one by one, and we want to do it in parallel. And also, we want to work on fast iterations, so you can iterate your builds and deploy your game on target device much faster. So with script only and data only builds. So basically, you could be able to fetch data on running player and introduce pre-process build attribute, which might give you flexibility when tuning different player settings, then kicking off build process. So that's pretty much all. If you have any questions, you can ask them at Ask the Experts area. We are run out of time right now, but thanks.